What's up, guys? We're going to look at electron shells today, and in particular, how it very much differs from what you were taught at GCSE. So this is a fluorine atom. Remember, fluorine has 9 electrons, and we would have learnt at GCSE, and we'd learnt at the first topic here, the first lesson here, sorry, that we've got 2 electrons in the first shell. We've got the next 7 electrons in the second. We can fit up to 8 in our second shell, 8 in our third, etc., etc. It's not quite as simple as that because this is broken up into subshells. And this is what our sort of subshells look like. For this second shell here, we have 2 sets of subshell. Our 2s subshell and our 2p subshells. Okay. Each of these, this can fit 2 electrons in, and the 2p can fit 6 electrons in. We can put it into this sort of context as well. We've got this idea of energy coming up, and we've got our shells sort of listed here. And we've got different shells. We've got s orbitals, which can fit 2 electrons, p, which can fit 6, d, which can fit 10, and f, which we don't need to worry about, which can fit 16. Okay, you need to become familiar with the sort of order of this, right? But luckily our periodic table helps with that. In particular, you should be able to see there's an interesting pattern here whereby the 4s has lower energy than the 3d. That leads to some interesting things which will make sense hopefully later on. So if we take the periodic table, we can split this into categories, right? So hydrogen and helium are sort of out by themselves, but they're showing here our 1s orbital, okay? Then the rest here, these are all of the rest of our s orbitals. So if we think we've got 2s here, 3s, 4s, 5s, 6s, 7s, etc. The next section shows our p orbitals. And again, that works the same way. Our 2p, 3p, 4p, 5p, 6p, etc. And our last section are our d orbitals. And oddly enough, even though here we have 4s, this is 3d. So 3d, 4d, 5d, 6d. And we don't need to worry about this, but this is our F block. Hopefully examples will make this clear, and we'll talk about these as exceptions later on. And you'll notice, again, we talked about 2 electrons in the s orbital. We've got 2 atoms, 2 elements here. 6 electrons, 6 elements. 10 electrons, 10 elements, right? So essentially, when we're talking about subshells here, we're talking about exactly where specific electrons are going, okay? And we'll go through some examples that hopefully shed a bit of light on this. So in terms of the rules, electrons go in the lowest energy available. Another rule here is that electrons ideally by themselves. And that's really because electrons are all negatively charged, so they repel, okay? So if we take fluorine as an example, right? So fluorine, we said, is F9. And so our electrons fill up like this. We've got 1, we draw a little half arrow pointing up and a half arrow pointing down. So this denotes what direction the electron's going in, what spin it has. Not too important for now, but we do need to show it in the right way. Next, 2s. Next, 2p. It's wrong, 5. And notice here, I'm going to go to the next box The next box will fill up first because electrons are ideally by themselves. Next box. So I've got 1, 2, 3, 4, 5, 6, 7 electrons. So our final 2 will go in the next 2 boxes. And we can write this out like this as well. So we've got 1s2. So that's showing we've got 2 electrons in that first subshell. 2s2, showing we've got 2 electrons in the next subshell. And then we also have 2p5, so that we've got 5 electrons in the next one. And again, we can use the periodic table to help us do that, right? So we've got 1s2, 2s2, 2p, 1, 2, 3, 4, 5. Okay, let's do another example of this. So if we go for calcium this time, we know that that has 20 electrons. So calcium has 20 electrons. So I'm going to carry on filling up from here, okay? So we've got 9 already, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we'd write it out like so. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. We can also do this in shorthands, where we go to our noble gases and we put that in square brackets. And what that denotes is everything that comes before it. So I'll write it out our 2 different ways. We've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And our other way, we go to our noble gas that comes before, which is argon, and we just put our argon in square brackets and do what comes after, 4s2. Okay, next rules. Now with transition metals, so in our D block, it becomes a bit more difficult. So we need to know 4s fills and empties before 3D. So what do I mean by that? So if we take scandium, Sc, and Sc+, if we take these as examples, we're going to just do shorthand for now. So I'm going to start off just by going straight to our Ar before. We get Ar, 4s, 2, 3d, 1. So Ar, 4s, 2, 3d, 1. Okay, now Sc plus will have lost an electron. Okay, in order to become positively charged, something needs to have lost an electron. And again, I think typically you'd think this would happen. We'd have Ar, 4s2, 3d, 0. But that's not right. As I said before, 4s fills up first, but it also empties first. So instead what we're left with is 4s1, 3d, 1. Okay, so super important we're following those rules. We also have a couple of exceptions. So we've got chromium and copper as our exceptions, and I'll show you why. And again, I get into the habit of labeling these straight away. So here, Again, if we go to our AR before, so we've got AR, let me make this a bit smaller. Now what happens here, we get to 4s1 first, and then 3d, 1, 2, 3, 4, 5. And really there, if we draw the electrons in boxes for this, like in our graph, all that happens here is that energetically, it just works out better that all of our electrons are like this. So this is one of the few examples that breaks that first rule, that electrons are in the lowest energy available, okay, or it appears to anyway. And copper is a similar thing, where we have, again, if we say AR, we have 4s1 again, 3d10. And again, this is the case there, where it just prefers that all of these d orbitals are filled and this remains empty. But then the rule applies where 4s will empty before the d orbital starts emptying. So really important that we know our exceptions. Okay, so let's do another couple of examples here. Let me change these examples actually, because I've already done that. So oxygen, first of all. Oxygen is here. I can use my periodic table to help. 1s1, 1s2, 2s2, 2p1, 2, 3, 4. 1s2, 2s2, 3p4. If I'm doing electrons in boxes for that, it will look something like this. It will look exactly like this. Our O2 minus, we will have gained 2 electrons. So this time we'll have 1s2, 2s2, 3p6. And it can help just to look, oxygen, if it gains 1, 2 electrons, it's going to have the same electron configuration as neon. And our electrons in boxes are going to look like this. Okay. Instead, let's do iron here and Fe3+. We'll do shorthand just to save us. So Fe is here. We'll start with the Ar. So we've got Ar, 4s2, 3d, 1, 2, 3, 4, 5, 6. Won't worry about electrons in boxes for now. And now Fe3+, Ar, we remember that rule that 4s fills first, but it also empties first. So it's 4s0. You don't need to write 4s0, you could leave that blank entirely. And in 3d5. Give these ones a go. But first, let me quickly go back to our previous. So remember, we've got this, first thing, mass spectrum of a protein. So it's electrospray. Therefore, this is MR plus 1. So my MR is 484. This will be due to a C13 or a H2 inside our protein. Okay, so this is our main thing, 484.1. Mass spectrum of a hydrocarbon. Again, we're looking for the big peak. This will be this will be electron impact. Sorry, this will be electron impact, and so we've not got any plus ones. So we're looking for a big peak, which is this, the highest big peak. That gives us 56. And again, this peak will be caused by something with carbon 13 or hydrogen 2. And these are fragment ions, right? These are where our hydrocarbon, say if it looked something like this, won't quite be this. It's where the electron gun has broken it here, say, and we've received like other signals. Last one, probably the most difficult. So bromine is Br2, as it says here. And we've got equal opportunity for it to be bromine 79 or bromine 81. Okay, so we can almost do a little probability charts. So we've got Br 79, Br 81, Br 79, Br 81. We can sort of add these up. So 79 plus 79, 158. 79 at 81, 160. 79 at 81, 160. And then 81 plus 81 gets us to 162. So 50% of our sample is going to be 160, 25% 158, 25% 162. So we draw that. Let's get something like that. Peak there, 158 gets 25%, and 162, 25%. Great. Happy revising, guys.